Okay, this is lecture 26 about finite free choice by Harvey Friedman. Please.
Thank you. Um, okay, so I spent most of my efforts since last week not doing checking, which is what I thought I was going to do, but more, I mean, some checking, but more looking to seriously simplify the new finite form. And I think that this is very successful, assuming that there's nothing wrong. I mean, I'll be able to tell I'm in the middle of verifying it. Uh, One of the nice things about it is it's very naturally and kind of immediately pi 0 1. So you don't have to you don't have to dance around uh, things. One of the interesting things about this is that there is an infinite form behind it, but the infinite form, which I pass through, but the infinite form is significantly worse than the finite form. The finite form is much nicer. So I think this is an interesting situation. There's a infinite form behind this, which I do pass through. It's good. It's important to pass through uh, on the way to proving the statement. But the finite form is obviously better than the infinite form, and that's not the usual case. So I think that's pretty interesting. All right. Um, so again, the chapters in the book. And as I told you last time, this is on my website in so-called final form, FINAL form. This is on the website now, downloadable manuscripts in final FINAL form. This is old and probably need a little bit revisiting. This hasn't really been done because I don't know exactly what this looks like here. And these two are yet to be thought through. I mean, there's some ideas already, but oh, excuse me, this is what we're doing now, and this has to be thought through from scratch. This here. So this has undergone quite a bit of, some serious change. This chapter, I'm calling it finite free choice. Um, I don't want to put too many words in there. I could put finite free choice with upper shift or something. I think I just call this finite choice. And I have an introduction that I haven't written. Okay, so as before, there's this section, this preliminary, this heavily set theoretic preliminary called elementary embeddings that needs to be done. That's important. And we'll go over that. I think I did some of that last time, but I think I have it more streamlined or maybe more accurate or whatever. Elementary embeddings, and then we get into the thing. So there's this thing, this section, the positive section is called free choice, and we have free choice functions. This is very general. This is the general stuff, not even in the rationals. This is in everywhere. And then we move the story into the rationals. And there's a thing called the upper shift, which has probably been discussed to some extent, but we have the upper shift and then the invariance condition, there's always an invariance condition. The invariance condition is going to be upper shift commutation, commuting with the upper shift. Um, and then I managed to use the elementary embeddings to prove the pi 0 1 statement, which is written this way: order invariance slash free choice slash finite slash upper shift. And then the reversal, so that's the positive part because elementary embeddings come from con SRP. So we proved this from con SRP. And now the reversal is a whole section. The reversal passes through first an infinite statement. Um, when I was talking about when I prove this, it passes through an infinite statement. I was talking about the positive direction, and that infinite statement isn't mentioned here. It's mentioned only in the text. It's mentioned only in 533. An infinite statement, an intermediary, which is not nearly as good as the finite form, which is this one, the finite version. Okay, now there's another intermediate statement I use in order to do reversal. And perhaps this isn't wise. I call the whole section by the name of this intermediary. Uh, that's not ideal. I usually uh, yeah, I think it's all right. Yeah. Well, the it doesn't highlight the drama. I think, yeah, we're just talking about what the table of contents looks like. We're not talking about content. Um, yeah, I may pull this out and call this another section 5.5. Okay. Anyways, that's an expositional issue. Anyways, so we wind up with our result, which is that this statement is equivalent to con SRP. Um, the point is that this statement derives these resolution sequences exist, and the resolution sequences give you this statement up here. You see. All right. Now there's a totally separate development. Now this statement involves very neat single functions. This is about a single function, and this statement is my other pi 01 statement, or pi 02 maybe first, pi 01, whatever. This one has a different flavor. First of all, the infinite form is an infinite sequence of objects, and the finite form is a finite sequence of objects. And this and you play on the fact that these lengths can be hefty. Um, this also has some serious merits. So I don't necessarily prefer even the first one over the second one. That's an issue, an interesting issue. But definitely from the point of view of computer science, this algorithm, this finite sequential free choice rotation, this is a non-deterministic algorithm that's rather has it looks like some sort of elementary computer science uh, uh, process, non-deterministic though. And so therefore, this may have some special significance in terms of the possible impact of this development on existing fields, namely theoretical computer science. So this is a very important development, I think, assuming this is right. Now, this is the one I've done the least checking. I haven't really gotten to. I checked. I sort of saw that I could probably do this in my head, but that's usually not quite sufficient. Um, so I expect. I'm thinking that maybe next time I might get beyond all this, although that's a little less clear, and get into this. If not, it would be the lecture after. Okay, So, and then I'm thinking, right now, I'm thinking that maybe this is enough of finite free choice, and my other finite stuff should be the games. The games actually have an interesting amount of leverage on various things, uh, board games and stuff like that. All right. So let me make a confession here. So the way I did the infinite case last time, I did an infinite form, was seriously wrong. I was dealing with choice functions of this form, which I now call total. And you can't use that with the upper shift invariance. So it was actually something wrong that was done last time. Uh, and I like to keep that. I don't care about the lecture being wrong or partly wrong or the notes being partly wrong. That's part of the historical record because everything's getting corrected anyways. And it shows the evolution of the struggle, the struggling evolution, which is actually some people think that's more interesting than the correct stuff. But I think the correct stuff is probably more interesting. All right, so you only get a choice function f from e to the k into e to the k for certain infinite e with the required properties. And this has a pi zero. Um, let me do something about this. Just a second here. All right. There we go. And this has a pi 0, 1 form, which is actually much better than the infinite form. Because I have to put some conditions on what capital E looks like. And this is this better finite form. This is our baby here. That's our baby. After the needed set theoretic preliminaries about elementary embeddings, I start with some elementary preliminaries about general choice functions. General choice functions. Then I move into the rationals where I bring in the upper shift function and upper shift invariance, which takes a particularly nice form of upper shift commutation. Then I transfer from the elementary embedding uh, yeah, into a dense in itself E contained in Q under the upper shift using threads. Maybe you know these threads from elementary embeddings. You take a point that you can't take the inverse of, you can't take J inverse, and it starts a thread going forward. Then I take a suitable finite piece of E to establish my baby. It's my baby here. And the reversal is section 5.4. All right, so with the elementary embeddings, there's this statement. There is an elementary embedding. Some of this is a review from last time. There's an elementary embedding F. Well, I'm eventually calling it J. J from M into M with critical point where M is a countable model of ZFC plus V equals L. Now, why am I talking about only SRP here today and not measurable cardinals? That sounds like a measurable cardinal or something like that. The answer is that this J is an outside elementary embedding. This J is not internal it's not internal to M. Not internal. All right. Now we're going to prove elementary embedding in WKL naught plus con SRP right now. And we work in WKL naught and assume con SRP. And we use the formulation of SRP involving subtle cardinal hierarchy, um, which we review from chapter 5, appendix A. Now, well, I was going to put the appendix, attach the appendix. The appendix is attached to chapters 3 and 4, actually. Yeah. We copy the main relevant definitions from there. So we have the definition of regressive. I think we've been over this. It's kind of boring. Regressive function from the unordered K tuples, from the K element subsets of lambda into lambda. And we have F homogeneous, if and only if when you have two B and C, then F of B. I'm sorry, but that doesn't. What did I do here? Uh, isn't it F of B intersect B intersect C equals F of C intersect B intersect C? Oh, wait a minute. Oh no, I think this is right. It's going into a finite set of ordinals. What am I talking about here? Oh yeah. So this is a regressive function into ordinals, not into sets of ordinals. Yeah, into ordinals, not into sets of ordinals. Yeah. So that's right. So it's constant on the K elements of sets of E. Right. Yeah. Oh, yeah. This is the other notion. Right. This is the other notion where it's into a subset. And then you have regressive takes this form, and you have F of B intersect the min of B union C equals F of C intersect the min. Yeah, which is an ordinal, which is a set of ordinals. Okay. Lambda is K subtle if and only if the following holds. You have a closed unbounded set, C, and regressive F. There exists an F homogeneous set of cardinality K plus 1. Yeah. And then STL is just where you have the K subtle cardinals exist for every K. Okay, SRP and STL are logically equivalent theories, and that comes from Appendix A. And oh, here, yeah. So the definition of K subtle, you only get a homogeneous set of cardinality K plus 1, right, in the definition over here. Well, you can ask for a homogeneous set of cardinality omega or higher, and it turns out you can actually get that. It's a little surprising, but you can actually prove that you can get that. And you can get it of any cardinality whatsoever less than lambda. But we only care about getting it of type omega. Okay. Now, the objects we really care about are these sets of indiscernibles. So an SOI of K is an omega sequence of cardinals, such that the following holds if you take the union of the cardinals. So it means that I have indiscernibility with respect to statements over V of mu, over the cumulative hierarchy on mu, right? And if I have two tuples of length K, um, it should be epsilon here. Okay. That's the usual kind of strong indiscernibles. All right, so now uh, if lambda is k-subtle, then I can find one of these gadgets of length omega. And actually, we can have an additional property that each one is an elementary substructure of the next, of the later ones. Okay, now that means that I have these things, but the trouble with these is that the arity is fixed. In other words, I have really good stuff and they're even well ordered. But it's only for fixed dimension, and I need to have them for all dimensions at once. For all dimensions at once. And in order to get that, I'm really going to use non-standard integers. See, non-standard integers come in. Let T1 be the theory in epsilon equals C and D with the axiom ZFC plus V equals L plus the scheme that D is a finite ordinal with at least K elements. This is just a particular way of forcing the models to have non-standard integers. That's all. Plus C is D subtle. All right, T1 is consistent because every finite subset is. Um, yeah, in other words, C is D subtle. So it's non-standardly integerally subtle, which means that I have plenty of subtle cardinals of every level, right? Because I have one of non-standard level. And how do I know D is non-standard? I know that D is non-standard because of this axiom. Excuse me, axioms, plural. There are infinitely many of those. Okay, and T1 is consistent because of the earlier thing, right? Because if I have any finite subset of this theory, it just refers to things that are outright true of the ordinals, well-foundedly true. Okay. All right. Now there's a theory T2, which is richer and which really gives us everything we want. It's a theory in infinitely many constants, which are going to be like our indiscernibles, with the following axiom: ZF Z plus V equals L. Very convenient to have in a context like this. The orbitals are increasing. Uh, for all I and j, V C I epsilon satisfies ZFC plus V equals L. Well, probably this J doesn't make any difference. Yeah. Okay, and this other one is elementary substructure, which is a scheme. And in fact, again, there's no J here. I don't know why I did that. Okay, now we have the indiscernibility for the formulas with it most the free variables V1 through Vn plus 1. Okay, suppose I's and J's are strictly increasing of length K, then we have this indiscernibility. This is just the indiscernibility we're looking for. So we just put it in the theory. I claim that T2 is consistent, and the T2 is consistent comes from every finite subsist every finite fragment is consistent. And that is not a problem. You see, this is fine. Um, yeah. You want to say that these C's do the elementary substructures, but you can only go, it's only obvious you can do it at finitely many levels. Besides, these fees, they're infinitely many formulas to worry about also, and the area n. So you do want to talk about finite fragments, I think, for this too. Right. Because it's the same C's that are going to be good for no matter what K. All right. So T2 is consistent. And so that means T2 has a countable non-omega model. I mean, it's got a countable model, but it's got to be a non-omega model that we've seen before. We've seen that before. Uh, yeah. Let's see. Where do I get the non-standard model because of that earlier axiom? Yeah. I don't know if I have to repeat it. Probably. Um, Second, let me think about this. Yeah, T. All right, I left out the proof here because I have it in the other manuscript, but in these situations, there's no problem making sure you've got a non-omega model. The problem is how do you know you can get an omega model? And we don't even want an omega model and can't get it anyways. So that's not an issue. Um, Clarify that more in the manuscript final thing. Okay, so we call this the non-standard SOI less than omega because K is arbitrary. And we write M equals AR C1 C2 dot 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 and I equals CI I less I greater equal to 1. We define now this stuff has too much in it, and it may this structure, the C's may not be unbounded in A. The C's may not be unbounded. They might form a cut below, the ceiling of AR, and that's not good. We pass to a definable substructure, except not the full definable substructure, just the def prime structure, which is the set of all x in A, the set of all points in the domain, which are definable with parameters from I and elements, arbitrary elements from V of C1. See, the first indiscernible, that hunk of stuff, lower rank, uh, you're allowed to define from it. And from any of the constant C, any of the C's. That is definition of def prime. Def prime here. Now, M is said to be regular if and only if every ordinal of AR is less than some CI. In other words, regularity just means that the CIs are unbounded. So let M be a non-standard model, a non-standard SOI of every arity. M prime is an elementary submodel of M, this structure here. Uh, maybe I didn't define M prime. M prime is made of the, oh, here it is. Yeah, sorry, I did define it. So M prime is an elementary submodel of M, and that uses V equals L. And M prime is a non-standard SOI less than omega with the same VC1. All right. Okay, so now we have the SOIs that we want. Uh, the C's are unbounded. We have V equals L. We have the indiscernibility that we want. Um, every point will be definable from the stuff in the before the first indiscernible. So now we're prepared to define the elementary embedding. Now we're ready to give the elementary embedding. For about this, and we go to this M prime, which is the submodel. So J from domain of M prime into domain of M prime is defined as follows. Suppose I have an X given, and it's the unique solution. It has to be the unique solution of a property. It has to be a unique solution to some property with parameters from C's and parameters from the stuff under the first indiscernible. Well, if I yeah, this is a mistake. I put the plus ones before I should. Yeah. So so this is a definition. This is a definition. And the y's are these low parameters. So I take J of X to be the unique solution to this. Same thing, except that I added one to the C's. It's exactly what I want to do. And now you have to prove that J is well defined, right? Because it wasn't defined in the most purest form, right? That J is well defined. In other words, if I have two different ways of picking out a point, then the way of picking out the point then the way of picking out the J of X, they have to be the same. Otherwise, this definition makes no sense. But that's clear because of the elementarity of J. Okay, and J is a mapping only from M prime into M prime. Right here. It's the elementary embedding with critical point C1, the identity below C1, and each J of Ci equals C of I plus 1, right? So the elementary embedding does what you want it to, and you can get this. And I just use ConSRP to do this. Here's a summary. Elem embed. ELEM/EMB. There's a countable model M of ZFC plus V equals L with an elementary embedding J from M into M, where the iterates of J at the critical point is unbounded. Okay. So now we're ready to go move on to free choice. Okay, so all right, so with free choice, uh, here's the setup, which I think I did talk about last time. Okay, first of all, double colon, I introduced that a long time ago, but we're going to refresh our memory. Double colon means partial function. This means f is a partial function from x into y when you write double colon. When you write single colon, the domain has to be x. Now, a relation on x is just a subset of x squared, and R is reflexive if and only if for all x in capital X, x R x, and R is contained in R contained x squared is symmetric if and only if x R Y implies y R x. Okay, now a choice function is just what you'd think it would be. But I'm now doing everything in the right generality, but they can be partial functions. So a choice function for R is a partial function in f from x into x, such that everything in the domain of f is related to f of x. Okay, a choice function. Now, to be R free means no two distinct elements are related. And a partial function is said to be total if and only if its domain is all of x. Okay. So there's this theorem that every reflexive symmetric relation on any x has a total free choice function. Total just means it maps x into x. And this is proved very nicely by a relevant extension lemma. So let R be given, and if I have a free choice function for R and I have a new point x, it could be an old point, but a new point x, I can always extend f to a large free choice function with setting the value of x to y. I can always do that and keep it a free choice function. And I can even require that y be in the range of f union singleton x. Very strong. Okay, so ZFC proves, from this, you can easily get that ZFC proves the total free choice. And in the countable case, you just need RCA naught. Because all you do is zonify this or start with a well ordering of everything. And then, yeah. You can zonify it, or you can well order X and just do the obvious transfinite recursion using the extension lemma. The extension lemma tells you how to continue. But how do you know you can complete it, even if you can continue? Well, that's transfinite induction or some zonification. All right, so we have a theorem that if f is a free choice function, yeah, this is useful. This comes up later. Free choice functions have some nice properties. One of them is they're idempotent. Okay. Secondly, the range is the same as the set of fixed points. The range is the same as the set of fixed points. Kind of interesting. And of course, these free choice functions are closed downward. So if f is contained in G, and G is a free choice function, then f is. Okay, so that's the end of the general theory. All right, upper shift. The upper shift is USH, which goes from Q into Q, which is the identity on the negatives and +1 on the non-negatives. And then the upper shift is extended coordinate-wise by taking it on each coordinate by this. Okay, now upper shift is meant to be used for invariance. And the way we use it for invariance is we talk about upper shift commuting, upper shift commuting. And upper shift commuting means that F circle for functions here, F circle upper shift equals upper shift circle F. Yeah. Now, we need to talk about upper shift commutation when F is not necessarily total like that. So here's the definition. A partial function is upper shift commuting if and only if the master equation holds whenever both sides are defined. Whenever both sides are defined, they're equal. That's the condition you need on for partial functions. All right. Now, certain arithmetic progressions come up nicely. I mean, this is a nice way of saying things. So AP of P comma Q semicolon N is the set of terms of the arithmetic progression whose first term is P, last term is Q, and has exactly N plus 1 terms. All right, so here is our finite form. Every order invariant relation on the arithmetic progression from minus k to k with nk factorial terms, well, plus 1, yeah, has an upper shift commuting choice function mapping 0 through k to the k into its domain AP minus kk 8k factorial. All right, I'm awake now. All right, so here is the statement. Every order invariant relation on this arithmetic progression has an upper shift commuting choice function mapping this basic arithmetic progression into its domain, which is this arithmetic progression. And notice the 8K factorial and the 9K factorial. No, I just was in the middle of checking this and making the computations. And of course, these numbers are overkill, and there'll be some more plain numbers to put here. But the basic idea is this one has to be somewhat finer than this one. That's a kind of an important thing when you unravel this thing. But anyways, this is obviously explicitly pi 0, 1 because there's nothing here. Oh, I said order invariant relation on this. This has to be the k-tuples, right? Yeah, has an upper shift commuting choice function mapping 0 through k to the k into its domain, which happens to be this, another arithmetic progression. See, this allows me to actually say some important things that in the infinite case, I would just have to say as side conditions. Uh, yeah, yeah, right. See, because I don't want I want the function to stay whenever the input is whenever the input is bounded by k, because the input is a tuple. Whenever the input is bounded by k, I want the output to be bounded by k, and that comes from the fact that minus k and k are there, both there, you see? This doesn't actually, no, this is right. Everything will stay below k and the whole thing, because that's the way the commuting choice function works, you see. That comes from the derivation, which we'll see down here, which we'll talk about down here. All right, now this is obviously pi 0, 1. In section 533, we derive our statement from elementary embedding, right? And then we have to reverse it. But we have to do this from elementary embedding. Okay, so we have this elementary embedding, and we make some definitions. So C naught is the critical point. And CI will be J to the I C0. Now, we have to densify. See, the best way to do this is not to use transfer induction on the ordinals of M alone. It's to cross product it with the dense 0, 1. We were doing that all the time in the chapter 3, by the way. We were always doing this kind of thing. But here it turns out that we also want to do it, even though I didn't originally think so. It causes some problems if you don't do it. All right, so we're going to look at this product, and this is the lexicographic product where this is the ordinary less than, and this is the ordinary less than. And less than star is lexicographic order. And then, as we did before in chapter 3 a lot, we also used an effectively given ordering on Q of type omega with left endpoint 0, all in the sense of M. And less than double star is the lexicographic ordering where you use less than for the first factor, but this order type omega thing for the second factor. You see. And then you extend this by max lex, as we did all the time in chapter 3. So there's remnants of chapter 3 here, but done only on a non-standard situation with non-standard integers. Before it was all in the ordinals. Okay, so note that less than double star is a well ordering of W, and less than double star prime is a well ordering of W to the K, all in the sense of M. And so now we can actually use this to do a free choice. So let R prime be so we want to transfer. It's the order invariant. If you have an order invariant definition in a reasonable place, it lifts and transfers to any other place, as long as it's linear or linearly ordered. Okay, so let F go from WK to W to the K be the free choice function for R prime constructed by transfinite recursion using the extension lemma. You see, you can do this because less than double star prime is a well ordering. You can do this. So this is the sort of natural free choice function. Okay, so what do we know about it? I mean, there's a lot of things we know about it. One is that it maps WK into WK is nothing. Is M definable without parameters, right? Because the whole thing is just a transfinite recursion, and W doesn't have any parameters either. And also we have this invariance condition, or actually commutation condition. F circle J is the same as J circle F. Now I've kind of used the fact that where it's defined, they're equal, because J technically is defined beyond W. J is defined on all of M. So my definition of upper shift commutation for partial functions kicks in here. All right, so, but I should point out that W itself is closed under F and J. All right, now this structure, so we want to look at this structure. W less than star restricted to WK. Actually, I had this convention that I don't have to say what you're restricting anything to, because you're just restricting to the fundamental domain, and you just use that strict sign. This structure is isomorphic to some E less than 0 upper shift restricted, where omega is contained in E is contained in Q. So now I'm saying that this countable transfinite thing in a non-standard model with non-standard integers is isomorphic, can be pulled into the rationals in such a way that the elementary embedding, which is a set of pairs, by the way, the elementary embedding J is sent to upper shift. You see, the upper shift becomes like an elementary embedding. That's the point. It's a mathematical elementary embedding. But of course, E is not very mathematical. E is a sort of a kind of mess, right? Just needs some E. All right, so we can fix F given up here and E given down here, and also the isomorphism H that does this. And then we can go further and just say that H is an isomorphism from this structure where all right, so I will do this game that we don't have to say we're restricting because it's understood. Um, an isomorphism from F from here, we don't have to restrict F because F goes from W to the K to the W to K anyways. To sum this, sum here, where G is an upper shift commuting choice function for R slash E, and less than E has left endpoint -1. So E has the smallest element, has min -1. Well, left endpoint, same thing. Okay, has min -1. Let's do that. And there are infinitely many elements of E between any two distinct elements of E. So E is dense in itself. I'm not asserting that E is dense in the rationals. That's something else, or even somewhere dense. I'm just saying that it's dense in itself. In addition, uh, for every x in E and n in omega, max x less than or equal to n implies max of g of x less than or equal to n. Now you get that, um, this is the g over here. You get that all because this holds in here. All this good stuff holds in here. Uh, because of the construction of F, the way we built F. We always lowered in a sense of less than double star, but less than double star when you're at a C. When you're at a C0, a C comma 0, uh, you reduce the ordinal there, you see. So you do have that. Probably I need to fix this a little. It should be C0 comma 0, I think. I'm not sure that I may want a different notation. Let's see. See what I'm saying? This should be, uh, yeah. See, maybe let's see how far back that goes. No, I think, yeah, here. It's actually in M. Yeah, there we are. Okay, I probably left the J. No, I kept the J. That's right. This one has to be also changed. Yeah. This is not important. It's just important to be, if you want it to be really accurate. Uh, yeah, because C00 is what goes to 0. Okay, and then you can actually prove the statement that we want. And I didn't finish this, but basically because of this Denson itself, you can just build the first couple of levels of Skolem holism, and the rationals can be moved around just to make sure that your numbers form arithmetic progressions. You see, that has to be written down carefully, but that doesn't seem to be any issue. Okay. And then I should probably end well, let me just quickly go just say all this here because I just want to take a few more minutes. Um, this is the bridge statement that's needed in order to do the reversal. This statement is a variant. This is a variant, and it's a simple variant of one of the statements treated in chapter 3. This chapter 3 was always in the interval -1 to 1, and this is in the interval -1 to k, you see? So when you divide this statement by k, you get the statement in the chapter 3. When you divide it by k over here and identity over here, which is still a perfectly good isomorphism. I'm sorry, this is not what I meant to write. 0 over k. This is not. This is what I meant to write. 0 through k. Yeah, this is what I meant to write. Right. And if you take this statement is equivalent to the one in that was treated in chapter 3, because all you do is divide these by k and make the identity on here, and you have a statement that's basically isomorphic to this statement. It's really isomorphic to the statement in chapter 3. So it has all the meta-mathematical properties, this one. Okay, so this intermediate statement, I have a powerful way of doing finite approximations to this statement, which gives me some other finite forms that are not anywhere near as good as what we're talking about. So they're not advertised finite forms, they're technical finite forms. And they talk about resolution sequences, which are ways of approximating this thing. And so if you have arbitrarily good approximations, arbitrarily good approximations, i.e., resolution sequences, you get this whole statement up here, which means that's strengths. Now, these finite approximations can be gotten from our baby. That's what we have to show. Have I done this again? Yeah, I've done this again. Yeah, then I show how to get arbitrarily long resolution sequences from the pi01 statement, under question that we're trying to reverse. From there, I can get these resolution sequences. Now, all of this will be discussed in some real detail next week. I shouldn't be sidetracked into trying to make the statements any better. I think this is, let's just look at the statement again, just to be complete about this. Here it is. Every order. See, I could have said every order invariant relation on Q to the K, and you'd all know what that means, because it doesn't make any difference where you define an order invariant relation, as long as it has a reasonable amount of elements in it. They transfer. But why not make it explicitly pi01 by literally saying I'm working in this space, right? I'm working in this arithmetic progression. I have an order invariant relation on this arithmetic progression, this thick one. Then I get an upper shift commuting choice function mapping this thin little one into its domain, which is a somewhat less thick one. See, there are three arithmetic progressions going on here. I could have written this as AP of 0K semicolon 1, but I think maybe just this would be all right. It's obvious. You see, so that's the statement. And then this other one that I think is very important involving rotations and upper shifts, which we haven't talked about today, uh, is very good from the computer science point of view because it's an obvious non-deterministic process of a simple kind. Uh, so that's nothing to sneeze at. So this is quite different, though. The two of them are quite different, and I think that they're good. There's another big shoe to drop that's coming. Uh, I have a way which I haven't thought through carefully, and I don't want to get sidetracked until this is done. I have a way of, or should have a way, very pretty way. Now I've done this kind of thing before, but not as pretty. Tweaking this a little bit so that the choice function, even the finite ones, are somehow internalized. In other words, the choice functions are actually equal. They obey the choice functions also obey at the same time an identity. Uh, yeah, the choice functions actually have an additional property beyond the shift commuting equation. It's a more elaborate equation or another equation. I'm not sure how I'm going to do this, which internalizes it in some sense. And automatically internalizes it. I don't talk about internalization. And then the statement is going to be like huge cardinals. So we're going to have something like this. We're getting close. We're going to have at some point when I have to get some time to do this. We're going to have at some point something like this that's huge cardinals. And it just may be fooling around with some numbers. And I think that's going to be, pretty exciting. But that's not for this book. That's for book two. Book two is the bigger cardinals. All right, I think I'm done. Thank you.